What's going on, everyone? This is Dustin Stelzer with another episode of Electrician U, and today we are going to talk automatic switches. So, an automatic switch differs from a manual switch. When we talk about manual switches, this is a manual switch. It takes manual action for you to flip this switch. There's no way to wire this so that it'll automatically change states when you want a light to come on or something to happen. It takes manual action. So, an automatic switch is something like this. This is a contactor. You'll see these a lot in commercial applications and industrial applications, shopping centers, parking lot lights, anywhere where somebody wants to be able to program the ability for a time or sunset or something like that to automatically turn on a whole grouping of lights. So what's neat about a contactor is a contactor can have 3 separate circuits that it can control. So rather than this single pole switch having one circuit that it can control one light with, you can actually bring 3 separate circuits in here, and there's a coil on the bottom of this that has a completely different circuit. This is what you would call a control circuit. So you'd run one home run to this. You'd run a home run to a photocell or something like that, and then the photocell you would run to your coil. And the coil is actually quite literally a coil of wire on the inside of this that's around a magnet. And so there's another magnet inside of here that when you send current through this coil, it actually sucks those magnets together and it closes these contacts. So you would bring your home runs into the top 3 contacts here, and then from here you would bring like one of these out to parking lot lights, and one of them out to some recess cans, and another one out to like outside sconces or something like that. You can have 3 complete circuits through one device, all turn on at the exact same time. So that's the cool thing about a contactor. A contactor is essentially a relay, and there's a lot of different types of contactors. There's general purpose contactors, which is what this is. It's actually rated for motor loads as well as resistive loads. You can get lighting contactors. Lighting contactors are usually a lot bigger, same functionality. Some of them have latching and unlatching coils, so there's actually 2 different coils that you have to hit with voltage from 2 different sources. I'll hopefully do a video on that if I can get a hold of one. They're really expensive, so I don't want to just go spend $700 just to do one video and then maybe return it. I don't know. Maybe I'll do that. I don't know. But lighting contactors are a lot more difficult to understand and to operate and troubleshoot. This is a 3-pole contactor because there's actually 3 poles to it. They have 4-pole, they have 2-pole, they have 8-pole, 12-pole, and you can get contactors that are massive. So anyways, that's a contactor. It's just the ability for you to control this. You can even control it manually. You can flip a switch that sends power and hits this coil and sucks those contacts closed and passes current out to a bunch of different circuits. Or you can have a photocell hooked up to this. You can have a time clock hooked up to it. There's a whole bunch of different ways that you would use this. So the next type of automatic switch that I'm going to talk about is a cube relay. This is essentially the exact same thing as this contactor. The only difference with a cube relay is that with a contactor, you only have one state that this entire device can go in. All of these contacts in this one, these are all normally open. So in a de-energized state, like it is currently in my hand, there's no power hooked up anywhere to this. It's de-energized right now. In a de-energized state, these contacts between here and here are open. They call that normally open. And they only close once you send power to this coil that closes all the contacts and allows current to go through them. It's only normally open. They also make contactors in normally closed, but every single one of these contacts is the exact same. They're all normally open or they're all normally closed. So with an ice cube relay, you actually get the option These come with contacts that allow you to have both normally opened and both normally closed, and it allows 3 sets of them. So this is an 11-pin cube relay. There's actually 11 pins on the bottom of this, and there's 11 spots that correlate with these 11 terminals. And depending on how you wire each one of these terminals allows you the option to have normally opened or normally closed. You're still limited to 3 circuits, just like you are on that 3-pole contactor. But you can have different coil voltages. And if you want, say you want 2 different sources, 2 different lights, like parking lot lights and some exterior sconces, to come on at night, but for some reason the customer wants their sign to go off at night at a specific time when they're closed. They still want to have parking lot lights on because they want their employees, after they close, to be able to get out to their car at night without getting mugged or whatever. But they want the sign to come off because they want everybody to know that they're closed. So you would not be able to do something like that with just this contactor, because all 3 of the circuits are going to do the exact same thing. With this, you have 3 different circuits that you have the option. You can have 2 of them turn on, 1 of them turn off. Just how you wire this. So that's pretty cool. And the last thing I'm going to cover is just a standard relay. This is essentially a cube relay. It's the same thing. There's a bunch of pinouts. There's a coil. How you wire these, you have a couple of different options, but you don't have the same kind of options as you do with a cube relay. You don't have normally open, normally closed. These are all, on this specific one, these are all normally open. So you hit a coil, they're all going to close, essentially. But a relay is pretty much the exact same thing as a switch. It's more like a multi-switch, and it's meant to be programmed or meant to have logic to it so that you can use an outside source to control whatever you're putting through this, rather than having to walk over to the wall and hit a switch. So before I get started, I want to talk about some safety concerns. There are some things when you're working around automatic switches that you need to watch out for. Working on a standard circuit where all the devices are manual, it's pretty easy to just turn that circuit off, and the circuit's not just going to come back on while you're working on it, unless you get some homeowner that's curious or is just an asshole and wants to be like, oh, wouldn't it be funny if I turned this shit on? The dangers of working on a standard circuit in like a residence are pretty small. You can tell the homeowner, don't turn any of these breakers on, turn this one off, so I'm working on it. But with an automatic circuit, they're a little bit more difficult because you most of the time are going to have 3 circuits that are on this 3-pole contactor specifically. Plus you're going to have a control circuit. So you have 4 circuits that you're working with on this one device. So for some reason, if you go and turn 2 of them on, or turn 2 of the breakers off, but you miss a 3rd one, or you turn 3 of them off, but you forget about the coil voltage, the control circuit, you can still get shocked. So it's just a little bit more in depth to turn these things off. Plus, if you don't turn anything off, if you just go out into a parking lot, you get up in a bucket truck, you go up and you start working on this pole light because all the pole lights are off, you think, there's no worry, everything's off right now, I can work on this. And say it's like 5:30 at night, and all of a sudden the photocell out there stops seeing photons coming in. So it closes and sends power to that coil on that contactor. It's going to turn all the lights on while you're up there working on the shit. Same thing with time clocks. Time clocks work on the premise that they keep a clock ticking all the time. There's constant voltage that's going to this time clock. And once the clock spins a certain amount, it hits these trippers, and the trippers turn the circuit on and turn them off. They're constantly running off of a clock 24/7. So unless you know that you've gone and manually turned that time clock off, or you've gone to the breaker and shut those circuits off, there's a possibility while you're working on the circuit that things could become energized. So there's just some caution that you need to be aware when you're working on automatic circuits. Always, always, always shut power off. Or if you're working on something that has a photocell, disconnect the photocell, turn the breakers off. If you're working on a time clock that has a manual switch on it, turn that thing off. But again, just turning breakers off is the best way to go about doing this. A lot of times, guys that have been doing this for a while, they know how to work on these, and they feel a little bit more comfortable working on them when they're live. But just be careful out there, guys, and just know the dangers of working with automatic circuits. So now, the meat and the cheese of it. So the first thing I want to talk about is this 3-pole contactor. So what I'm going to do is I'm going to draw a panel. And we're going to draw the contactor. And I'm going to draw this contactor with 3 lines in and 3 lines out. That's going to represent the 3 poles in, 3 poles out. And then, just for ease, this is not how it's set up, but I'm going to draw a coil down here. And I'll just do plus and minus so that you guys can see that that's the coil circuit. And then out here, we're going to have 3 items that we want to turn on. So we'll call this a parking lot light. And we'll call this a sconce that's out on the front of the building somewhere. And we'll call, what else? We'll say that this is a sign. So we have 3 different things that we want to turn on through these 3 different circuits that we're going to run. And I'm even going to go as far as saying circuit 2, circuit 4, circuit 6. And we're even going to have to deal with circuit 8 because we have to get a circuit over to our contactor. So, how this in theory works is you would run your circuit 2 to the contactor, to one of these poles. You'd run circuit 4 to that same contactor on a different pole, circuit 6, same thing, and then you would run out to each one of the lights. This device is basically breaking the wire that goes straight from the panel all the way out to the load that you're trying to service with it. But the problem with wiring it this way is that this would make everything constant hot all the time. There's no extra device that tells it automatically to turn on or turn off. Circuit 8, I'm going to do this in a different color, just because I got all these fancy markers. So circuit 8 is you would wire to your coil, and then you'd have a neutral that comes back to the panel on a neutral bus, and that would give you 120. Every coil is rated different. This one is actually 208, 240, so this one you would need 2 hots for. So let me make that even less confusing. Let's say 10. We have to get 208 or 240, which means we actually do need two circuits. If we don't have 208 or 240 to this, if we run 120 to it and the coil is rated 208 or 240, it's not going to open and close. Depending on the brand and the makeup of these things, sometimes you might get a little bit of a chatter, but there's just not strong enough force to hold that electromagnet to suck it down and keep it sucked down. So we've got coil voltage that is going to suck these contacts closed, and since all of these breakers are on, this thing is just going to stay in a closed state all the time. So current's always going to be flowing through it. These things are never going to shut off. So what we do is we introduce a photocell or a time clock. For this illustration, I'm just going to do a photocell. So right here, we've got a bell box outside that's on the building somewhere. And on that, we've got a photocell. So what we would do is the photocell is the thing that is going to be controlling whether or not this coil opens and closes. These circuits are all going to run through the contactor, through these 3 poles. That doesn't change at all. It's just that what's run to this coil needs to have some sort of like logic or automatic switching means. So what we would do is we'd run one of our hots to one side of this coil. We would run the other side to a photocell. Photocell also has a little coil in it, just like this does. It's literally just a coil of wire. That's why we call it a coil. And then from there, it would run out and go to the other side of that. Now, every photocell is different. If you have a 120 photocell, you're going to run a hot and a neutral down here. But anyways, just so you understand the idea, the main concept is we're running power through a photocell to complete a circuit back to the panel. It is 208 or 240 in this case, because this is not a 3-phase panel per se. But you're using this photocell to open and close. When a photocell senses that there's light out, it stops allowing current to go through it. So it stops sending power up here, it breaks the circuit, stops sending power up here, and it reopens. This button on the inside actually pops back open to let you know that this is in a de-energized state now and no current's going to be flowing through it. But at night, when this photocell stops sensing photons coming into it, it'll actually it'll lock its coil shut, it'll send power through, lock that coil shut, and it'll allow current to go through all of these, because this thing will suck down the magnet inside. It'll suck the contacts, and it'll connect this one to that one to that one, and that one to that one. That's how this works. Pretty simple. You may have to watch that again if I was a little bit confusing or cryptic. I apologize. But let me know if you have any questions on this stuff. Message me, leave some comments below, email me, whatever. But that's the basic gist of a contactor. So now we're going to go a little bit deeper. And I'm going to do this one 120 on the coil. So this is a cube relay. Cube relays, if you look on the side, there's actually a certain pinout, and there's a wiring diagram or a schematic that shows you exactly how the pinout on this thing works and how you're supposed to wire it to get the results that you want. So let me just draw. All right, so the pinout on these, we're going to have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. And to go along with our schematic, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Again, this is an 11-pin ice cube relay. They come in 8-pin. There's different versions of these based on what you're trying to do. But for this one, I got an 11-pin because it's kind of similar to the 3-pole contactor that we were just talking about. So on every single one of these, you're going to have 2 and 10 be your coil voltage. So I'm going to draw a coil. Just like on the contactor, remember this contactor has a coil in there. Between 2 and 10 inside of here, there's actually a coil. So then you're going to have 6, and I think, what was it, 9, no, 1 and 11. Boom, and boom. All right, so then this is going to be normally open. This is going to be normally closed. Nope, I said that backwards. This is going to be normally closed. This is going to be normally open. When I say that, I mean normally closed means that between pin 8 and pin 11, we have continuity. They're already closed in a de-energized state like it is in my hand right now. No wires hooked up, no power running through it. In a de-energized state, number 8 is touching number 11. It is already closed, normally closed. So I'm going to write normally closed. Normally open means that when this thing is de-energized, number 9 and number 11 are not touching. But when I send power to that coil and close this thing, this 11 contact, there's a flapper that actually moves down, and it makes connection with 9 and it sends it through to 11. Then 8 would no longer be connected. That would open. So we have a few sets of those. We actually have 3 sets of those, which is really the cool part about these ice cube relays. There's 3 different loads that I can serve because I have this same setup. Because that one, that's closed. And that is open. Normally closed, normally open. Normally closed, normally open. Okay, so this is a little bit more in depth of a schematic. A lot of stuff going on, but essentially it's the same thing. If you look at this area, this is one pole, similar to on a contactor, how you would have one pole here. This is a separate pole, so you'd have a separate pole. This is a separate pole, there'd be a separate pole. the idea is that with each pole you have the option of going normally closed or normally open without it affecting any of the other loads being served. But the reason that we're using an 11 pin ice cube relay, the reason that we're using an 11 pin is because it takes 3 pins for each one of the loads being served. It doesn't take 3 pins. You just have 3 pins as options for one load. So these 3 pins correlate to one load, these 3 to another load, these 3 to another load, and then your last 2 are always your coil. It doesn't change. Even on an 8-pin contactor, you're still going to have 2 that serve as your coil voltage, and then you're going to have 6 that are for 2 sources, 3 for one source, 3 for another source. So if you have 3 loads being served, pick an 11-pin ice cube relay. If you only have 2 loads to serve, pick an 8-pin. You can use the 11-pin still and just have some unused shit on it. That's fine as well. But anyways, that's why they make them the way that they do. So now let's get some fanciness in here. Let's draw some pictures. So let's say one of the loads that we want to serve is going to be a sign. We talked about a little bit earlier about this customer wants us to come in and somehow make their sign at night turn off, and they want all the outside lights to turn on. And they have 2 different types of outside lights. They have parking lot poles, and they have exterior sconces all the way around the building. So this is going to be our parking lot poles. Shining light out beautifully. And let's do some kind of like fancy decorative half circle cylinder Texas star sconce that shoots light out of the top and shoots light out of the bottom. For some reason in Texas every fucking light fixture has a star cut out of it. We're the Lone Star State. Love our stars. People have light fixtures that are in the shapes of stars. So this is Texas. We're going to have a star light fixture. Alright, and the last thing that we want is... Oh, you know what? I'm an idiot. I'm sorry. I need to draw this up here. Boom. Alright. So, pole light, sconce, sign. This is going to be our setup for the sconce. This is going to be our setup for the pole light. And this is going to be our setup for the sign. So what we do, we could wire all 3 of these to 1, 2, and 3, but we don't have any coil voltage. So again, we have to hit the coil with a control circuit. I'm just going to do 110 on this so I can show you a different variation of how this works with 110 instead of doing like circuit 8 and 10 like I did a minute ago where it's 240 or 208. I'm just going to do it in 110. So for this to all work, we still do have to have a photocell. Let's draw in black a photocell. So right here, we got our bell box outside somewhere on the building. We've got a photocell. So for us to get this to work, we want the photocell to be energizing this coil to this coil. When the sun goes up, we want it to de-energize, and when the sun goes down, we want it to energize. So we would run our circuit 8 to this. It's going to have, let's just say this is the neutral bus. You're going to have a neutral that goes with it. This thing has a neutral that goes into the same wire nut. And then you're going to have one more wire that comes out of the other side of this. And that's the wire that's going to go to number 2. Now out of this side, we still have to get a neutral back to our panel. So we get a neutral back over there. Sorry, I should make that dotted so that you know it's neutral. Stay consistent, right? I don't want y'all bitching at me because I'm being confusing. Okay, so that all makes sense. You're running your hot through your photocell, bringing it out to the coil of the ice cube relay. You've got a neutral that comes back, that completes the circuit. When you blind this photocell, or when it's nighttime, it's going to allow current to go through. When it's daytime, or you take the tape off, It's going to stop sending current through. It's going to de-energize this thing. Now for the actual loads. Let's go with a different color. Let's go with blue. Ah, shit. No, I already started with red. Just kidding. All right, so think about this for a second. How do we wire this? Which home runs do we run to which sources? And do we need to run them to normally open or normally closed? So let's think about it for a second. If we run a hot wire out to normally closed, this thing is going to be de-energized most of the day. So if I wire this normally closed and it comes through here and goes out to the light, during the day when this is de-energized all the time, it's going to stay constantly on. So we know that's not right. We don't want to wire it to the normally closed one. When this thing is de-energized, we would hook it up to normally open because, again, there's no current being passed through. This light will stay off as long as this is off during the day when the coil is de-energized. So we want to run our home run to 7 under the normally open contact. We want to run the other wire from 6 out to our pole light. That way, during the day when this is de-energized, there's no current going to those lights. But at night, once this photocell energizes this thing and sucks the contact closed, it moves that over to that normally open contact, and it closes the circuit. So you may have noticed all of that just changed. It's kind of the same. I just ran out of battery and didn't realize it and did this whole fucking episode. So anyways, I had to redraw everything. So what I was doing, we're going to take circuit 2, run it over to 7, then we're going to take 6 and run that up to our light. That's going to power the normally open contact. When this thing is de-energized all day long, this contact is normally open. It's not going to be shut. It's not going to pass any power through. When this energizes, because the photocell at night tells it to energize, it's going to change positions. It's going to close that contact and actually send power through to the light. So we're going to do the exact same thing to the sconce. We're going to take circuit 4, purple, and we're going to go to our normally open contact 3. And then we want to close the circuit when this thing energizes at night. We want to close that circuit, so 1 will be the contact that moves when that energizes. So 1 is going to go back to our sconce. So 1 to the sconce. Now the last one, the one that's a little bit different, I'm going to do in blue because I want to be able to differentiate what's going on over here. So these two lights are going to come on at night. All day long this thing is de-energized. The photocell's not turning it on, so this is de-energized. So we don't want lights on during the day. We want there to be a gap. We want this circuit to be open. But when that photocell kicks, we want both of these to shut. Well, at the same time that happens, when this energizes both of those shut, this contact is going to change also. So in the terms of, when this thing energizes at night, we want this thing to shut off. So we're going to wire this the opposite, because all 3 of these contacts, 1, 6, and 11, are all going to change positions from where they're at right now. So this one, all we're going to do is wire it backwards. So just to make this a little bit easier to see, I'm going to go 6 all the way to our normally closed contact, and then we're going to go from 11 all the way over to our sign. So just see how that's different. Both this circuit number 2 is going to normally open, circuit number 4 is going to normally open, and circuit 6 is going to normally closed. So during the day, normally when this thing is de-energized, circuit 8 is going to feed through to circuit 11, and that's going to feed out to the sign all day long. But when this thing energizes, that contact moves to normally open. So it's actually going to open that circuit while it's closing that circuit and closing that circuit. All that stuff's going to happen at the exact same time. So that's how you would successfully wire an 11-pin 3-circuit ice cube relay. So with these devices, these poles can be rated at different voltages. You can have up to like 600 volts. I think this one will do up to 575 volts. The coil is rated at 208, 240, but you can actually get different coils for these. You can get one that's 120. You can get 12 volts, like the same thing with the ice cube relays. You can get the coil to be all kinds of different volts. So if you're working in a cabinet that only has 12 volts available, you can get a coil that's 12 volts. Get low voltage control circuit, but you can still run 480 through the thing. So there's a lot of flexibility too, just depending on what environment you're in and where you're working with it. But let me know if you guys have any more questions. Automatic switching, really badass. It's a lot of fun to think about, and a lot of fun to work on and troubleshoot. It can be a pain in the ass when you don't really know what's going on, but doing it enough times actually really helps. Getting your hands on it, getting tools turning, and like just wrecking your fucking brain about it all really helps. So hope that helps, guys. Leave some comments below. If you like this shit, turn the little notification thing on so you get notified every time I'm going to do an episode. And interact, man. Go to the Electrician U on Facebook, Instagram, Twitter, all that jazz. Get at me. Love you guys. See you in the next episode.